Good morning and welcome to this next lecture on sound and structural vibration. If you recall, last class we were looking at sound radiation from a single cell have a plate or panel vibrating in a mode, a single mode, with a certain PQ. Okay. And we are looking at sound radiation from one cell out of that, and we computed time averaged far field intensity, sound intensity. Okay, that is this expression. That is this expression from one cell. Okay. Now I will remind you I will show you this picture. This is the value over the whole cell at low frequencies. I mean, this is the value over the entire plate. This is the sound intensity in the far field from the entire plate at low frequency. Okay. So you will see that both are the same. Twice rho c magnitude Vp square KAB by pi cube RPQ whole squared. Okay. So let me go back here. Twice rho c magnitude Vpq squared. Okay. Then KAB by pi cube RPQ whole squared. Both are same. So what the entire panel has radiates, the intensity is equal to what one single cell, okay, assumed as a monopole. Now which means what? What it means is, how do you compute finally the power, right? You compute power by integrating the intensity over angles, right, in the far field, right. So you will take your intensity and integrate over d theta d phi, right. Now this intensity we assumed cos and sine to be 1, okay. In the panel case we assume the maximum value, but actually it will vary with angles. So that means if we actually compute power from the entire panel, it is going to be less than, okay, what you get from one single cell, intensity from one cell, because in the monopole sense there is no variation in intensity over a hemisphere, okay. For the expression as a radiation from a single cell, there is no dependence on theta phi, whereas for the entire panel hypothetically we put cos and sine to be 1s, but actually they contain theta and phi variations. So we took the maximum value. So when we took the maximum value, the intensity was equal to what one cell radiates, but in actuality it is not maximum at all angles, so it will be less than that. So if you actually compute the power from the entire panel and compute the power from one single cell, what the one entire panel radiates is less than one cell. Okay. So, the whole panel is not amounting to one cell. That is the conclusion. Okay. So, what would that mean? What is the meaning of that? Okay. So, what that means is this. At the very first cut, that is what it means. So, I have this is a one wavelength, let us say, okay, one wavelength on the panel, maybe in the x direction, okay, and it is radiating sound. So, it pushes the fluid here and it pulls the fluid here, and that is how sound is radiated to some distance. Okay. And suppose the acoustic wavelength is this much, this is the acoustic wavelength. That means what? Lambda x is greater than lambda acoustic, which means k x is less than k, which is the condition for good radiation. Okay. This gave us the maximum at high frequencies. So, lambda x is greater than lambda, which means what? In some sense the speed of the wave on the panel is greater than the speed of sound in the medium. Okay. The panel wave moves faster than the sound wave in the medium. That is what this condition means. In the flip side, what happens? Suppose the acoustic wavelength is bigger. Acoustic wavelength is bigger. That means structural wavelength is smaller, which means what? This time lambda x is smaller than lambda. So, structural speed is slower. Okay. Then what happens? As this structure starts to push and it starts to pull, it is doing it slowly. Okay, it is pushing it slowly in comparison to the speed of the fluid, and so the fluid will try to find an escape route. Okay, the fluid will try to, if you try to push, it will try to find the path of least resistance and escape around the panel, and therefore at a distance the receiver point will not receive sound. There is a local cancellation. There is a local cancellation. Okay. Amidst the high regions and low regions of the panel, the fluid escapes. Okay. In contrast, what is it when lambda x is greater than lambda? The structural wave moves very fast and the fluid does not have time to escape. Okay. Fluid is slower in this case. Okay. So, the structure pushes and pulls much faster than the fluid can respond, and so the fluid has to be compressed here and the fluid has to be rarefied here, so that at some receiver point there is sound. Okay. So, that is what this means. We need a measure of sound. Efficiency. Okay. What that means is that two radiators having same vibrational power, okay, and one is efficient, and second fellow is inefficient. Okay. Now, how do we say that? Two radiators with the same vibrational power, one is efficient, one is not efficient. Okay. So, let us say that the wavelength of sound lambda, the wavelength of sound is of this dimension. Okay. And there is radiator 1 okay, and we will just plot the x directional vibration, okay, in x direction. So, let us say this is the x direction, this is the dimension of the plate, let us say this is A. Okay. So, let us say the vibration is like this. Okay. Definitely the lambda x is greater than lambda, right. That is when the radiator is efficient. And let us take radiator 2. Okay. And that is also having the dimension A, but this is lambda acoustic, right. So, let us say its profile looks like this. Okay. So, this happens to be the structural wavelength, okay, definitely less than lambda. Okay. Now, it is possible that its vibrational power is equal of 1 and 2 are equal. Okay. So, regardless of the vibrational powers being the same, the sound radiated is different. Okay. Now, what is the measure of power? Okay. If I have a signal x of t, okay, its instantaneous power is proportional to x square of t. Okay. So, then from there we can derive a mean square value. Okay. Mean square means what? Square and mean of it. Okay. So mean of square value. So just to mean square value is mean of square value. Okay, so that's the mean square value. So that's the indicator of power. Okay, so suppose I have a signal of this form: V tilde PQ sine P pi x by A sine Q pi Z by B cos omega t. Okay, this is the form of vibration on the panel. Okay, so I'll do a mean square value of this, mean square value. Okay, but it will be mean in the sense of space and in the sense of time. Okay, so we'll indicate this as a mean square value okay x, z and t. So what will that be? That will be 1 over t integrated from 0 to t, the time period. Okay, then 1 over AB integral of from 0 to A and integral 0 to B V tilde PQ square. Okay, we will consider this to be real anyway, right? Square, then sine square P pi x over A into sine square Q pi Z by B into cos square omega t, then you have dx dz dt. Okay, t is equal to twice pi by omega. Panel is vibrating at omega frequency. So if you compute this, this is going to be equal to V tilde PQ square by 8. Okay, you get a half from here, you get a half from here, and you get a half from here, and you get V tilde PQ magnitude square by 8. Okay, now that's your mean square velocity. Okay, now what is a good radiator? So consider a piston, a circular piston, okay, in a baffle, okay, radiating with velocity v n cos omega t. Okay, and at high frequency, where it is most efficient. The time averaged power is given by 1/2 rho 0 c into the area of the piston pi a square into Vn square. Okay, because there are no spatial variations. Okay, there are no spatial variations as the piston vibrates. If you have a piston in a baffle, okay, vibrating back and forth at Vn cos omega t, oscillating back and forth, it is Vn is uniform over the circular piston. There are no ups and downs as it happens in the vibrating plate. Okay. So, this is now the power, and this is the mean square velocity, mean square velocity only related to time. Okay. But now the panel has variations in space also, and therefore the mean square velocity is V tilde pq magnitude square over 8. Okay. So, now suppose we define a measure sigma, okay, as the power radiated by the panel at omega, okay, the averaged power, okay, time averaged power vibrating from a vibrating panel, okay, as the numerator, and in the denominator we put rho 0 c area. This area is the same as the area of the panel, and V tilde pq magnitude square over 8. Okay. So, now this gives a measure where only cancellation is accounted for. Is accounted for. Okay. So, the denominator is the radiator radiating into the same medium, has the same area, has the same mean square velocity, and so does the numerator. Okay. But it so happens that the numerator has volume velocity cancellations, and therefore it will radiate less. Okay. Now, there is a paper by Wallace which we will see in some detail later, and that is what it does. It computes numerically the radiation efficiency using this measure above, okay, using the measure above, which is equal to the numerically computed power from a rectangular panel, mostly with simply supported boundary conditions, and this denominator rho 0 c area into V tilde pq square over 8. Okay. This is of course computed using the Rayleigh integral, and then the power over the hemisphere, power computed over the hemisphere. Okay. If you do that and we plot, there is a non-dimensional frequency here which I will explain a little later. Okay. So, let us say that non-dimensional frequency attains the value 1 here, and the sigma is plotted over here, then you will get these pictures. Radiation efficiency is 1, sigma equal to 1 here. So, you will get an increment with frequency okay, and something happens here, you can go above 1 also, okay. You get these sort of pictures, okay. So don't worry about this portion here exactly, okay. This measure sigma can be greater than 1, okay, but don't worry about it for now. We'll talk about it maybe little later, okay. But the main feature is that as frequency increases in this direction, the radiation efficiency goes up, okay. So what is happening is that initially okay, if you look at your panel, and let us say we are in some particular mode, okay. So you can kind of see that this is the wavelength in the x direction, this is x, right, this is x, and that is z, let us say, yeah, and this is the kind of wavelength in the z direction, etc., okay. So you start off at low frequencies where the wavelength of sound is much bigger, wavelength of sound is much bigger, okay. And so cancellations will occur, okay. So lambda x, lambda z, the panel mode wavelengths are less than lambda, okay, the acoustic wavelength, and therefore there will be cancellations occurring of volume velocity, okay. So how the cancellations occur, we will see again a little later how the cancellation occurs. We will see a little later, but let us just say that cancellations do occur, okay. And then so you are somewhere here at low frequencies, so you are not so efficient, okay. These are modes, by the way, okay, any particular mode. Now as frequency starts to go up, okay, again the same coincidence picture starts to come in. Your acoustic wave number goes like this and your structural wave number goes like this, okay, and you are somewhere in this region, okay, where acoustic wavelength is less or acoustic wave number is less or acoustic wavelength is higher. And as you go up in frequency, the wave number behavior is, you know, square root omega and directly proportional to omega here, okay. The same thing happens. So somewhere you will have lambda x and lambda z approach lambda, okay, so that the cancellations are reducing. So maybe you are somewhere here in this region, and then finally when you cross this non-dimensional frequency of 1, okay, lambda x and lambda z, they cross, okay, they become greater than lambda and the cancellations stop. No more cancellation. That means now your panel is at its most efficient radiating condition, okay. So this picture captures that cancellation effect. This picture entirely captures that cancellation effect, okay, and therefore sigma is a good measure, sigma e is a good measure or reasonably good measure. Okay. So, it is the sound radiated in the far field by a single mode at a single frequency. Okay. The time averaged power radiated divided by the power radiated by a piston, a circular piston. Okay. When it is most efficient in the same medium having the same area as that of the plate, okay, and the same space time mean square averaged velocity. Okay. So, we are out of time. So, we will continue from here and we will look at what is the cancellation nature. Okay. We will do that in the next class. Thank you.